My name is Habeeb Ur Rahman Mohammed. I am an applications engineer with Texas Instruments High-Speed Products Group. In this video, we will understand ripples in RF device performance measurements, unmatched and improper interconnects, cables, connectors, SMA launches, and the board traces cause impedance mismatch, which results in multiple reflections of electromagnetic fields and leads to the formation of the ripples. These ripples results in measurement errors of the RF performance such as gain, output power, linearity, and return loss. Consider a basic transmission line with source Vs and source impedance Zs, load impedance ZL, and the transmission line characteristic impedance Z0 as shown on the top side of this slide. In order for an input incident wave to travel completely without any reflections, the transmission line should be matched to the source and to the load. If the transmission line, which could be a coaxial transmission line shown here on the left side of this slide, or a microstrip transmission line shown on the right side of this slide, has the characteristic impedance not matched to either the source or to the load, then there will be reflections at the plane of mismatch. This plane of mismatch could be considered as a boundary of two mediums with different dielectric properties shown on the bottom left side of the screen. Considering the source and the load 50 ohms impedance equivalent to the absolute permittivity epsilon 1 and the mismatch transmission line characteristic impedance equivalent to the absolute permittivity epsilon 2, then the two planes of mismatch can be considered as an equivalent dielectric block shown on the bottom right side of this slide. Reflections due to impedance mismatch can be better understood by looking into electromagnetic wave interaction at the impedance mismatch planes. Interaction of the electromagnetic waves at the mismatch planes leads to the reflection and transmission of waves at the boundaries of medium, which is quantized in terms of reflection and the transmission coefficient. The reflection coefficient is the ratio of reflected to the incident electric field strength, and the transmission coefficient is the ratio of the transmitted to the incident electric field strength. These coefficients are related to gain, output power, linearity, and return loss. Any ripples in these coefficients will appear in the device performance parameters. Thus, we will see ripple formation in these coefficients due to multiple reflections. Let's consider multiple reflections scenario with multiple reflections at the boundaries of mismatch, that is from medium 1 to medium 2 and from medium 2 to medium 1. With the electric field incident on the first boundary of medium, some of the field will get reflected and some will get transmitted. The total reflected electric field will be sum of individual reflected fields. It is given by this equation. Here, gamma 1,2 is the reflection coefficient from medium 1 to medium 2. Therefore, the reflection coefficient with multiple reflections, which is the ratio of total reflected field to the total incident field, is given by this equation. Similarly, the total transmitted electric field will be sum of individual transmitted fields and is given by this equation. Here is the transmission coefficient with multiple reflections. Now consider hypothetical scenario with the incident wave only reflected from the first boundary of mismatch plane and transmitted completely from second boundary of mismatch, that is, no multiple reflections within the dielectric block. The reflection coefficient without multiple reflections is given by this equation, and the transmission coefficient without multiple reflections is given by this equation. This figure shows the plot of reflection and transmission coefficient equations with and without multiple reflections. For illustration, the dielectric block with relative permittivity 10, length 10 cm and medium 1 with relative permittivity 1 was considered. It can be seen both the solid red line reflection coefficient with multiple reflections and the solid blue line transmission coefficient with multiple reflection show ripples, whereas the dotted red line reflection coefficient without multiple reflections and the dotted blue line transmission coefficient without multiple reflections do not show any ripples. Here is ADS Advanced Design System software simulation. A 50 ohm microstrip line is considered, and it can be seen the transmission coefficient of the microstrip line do not show any ripples. In the second circuit, a 30 ohms resistors were deliberately added to create a mismatch at input and output. The blue line is a transmission coefficient with 30 ohms resistors and is around minus 10 dB, as most of the power is reflected due to mismatch, but it can be seen it shows a rippled response. This is network analyzer, which measures reflection and transmission coefficients. Here is the evaluation board with simulated 50 ohms transmission line, and 30 ohms resistors are placed intentionally at input and output. Let's see the transmission coefficient of this transmission line. And you can see the transmission coefficient shows a rippled behavior. This slide shows the comparison of the measured and the simulated transmission coefficients. Thus, care is taken while measuring devices at RF frequencies, and RF engineers make sure measurement setup is properly calibrated and matched in order to avoid measurement errors due to ripples from the mismatch. Thanks for watching this video. Please follow the URL at the end of this video for more information.